afternoon. Welcome, everybody. Welcome to the last talk of the event. First of all, I want to thank the committee for inviting me to be the session chair of this interesting talk. I'm pleased to announce the talk entitled Declarative Language for Geometric Pattern Matching in VLSI Process Rule Modeling. And it will be presented by Gyuszi Suto from Intel. Gyuszi graduated in 1987 from Technical University of Cluj-Napoca in Romania. From 1987 to 1993, he worked in various companies developing physical design CAD and compilers for supercomputers. In 1993, he joined Intel Corporation in Hillsboro, Oregon, USA. There, he has been involved in VLSI physical design ranging from placement, routing, and design for manufacturing. Since 2010, his focus has been VLSI design rule modeling for advanced nodes. He was also part of the C++ standardization effort in 1998. And at Intel, he taught C++ and organized yearly programming contests and SW conferences. Gyuszi, you should have about 50 minutes to speak. In the end, we will have a round of questions. If anyone in the audience has a question, you can type in the YouTube chat and I'll address them to Gyuszi. So please go ahead.
Thank you for the introduction. Just to clarify, I have 50 minutes, 50, right? 50 minutes.
I think so.
Okay.
Yeah, around.
Around, yes. Can you see and hear me okay? Can you see my presentation? I'm going to switch presentation mode. Can you see and hear okay?
Yeah, it's okay, perfect.
Yeah.
All right, very good. Okay, well, thanks for the invitation. I did visit Brazil a few years ago, and I was very pleased, and I really liked it there. I want to go back one day. So thanks for the opportunity to present this virtually. This presentation I'm giving today is based on a presentation I gave last year at the International Symposium of Physical Design. And this is a result of a work by 7 colleagues of mine. One of them, the last name is Renato Hinchke, who is graduated from UFRGS, and I think he's online now. So this is a result of a multi-year effort I'm going to present here today. So I want to start with regular expressions. I assume that most of the audience knows what regular expressions are. If you don't, in the pink there, let me turn my laser on. This one is a pattern of interest for if you have some text file and you want to search for certain strings. Can anybody from online just answer how many of these three patterns, words will match this pattern? If anybody knows, just type it into the chat window. The answer is 2. 2 of them will match. And why will these 2 airplanes match and this one won't? Because what we wrote here in the regular expression with these symbols, with the square brackets and the question mark, what it means is that we are looking for an uppercase A or lowercase a. This is the OR between A and A. There's an OR between I and E, followed by an R. And this O followed by question mark means that either we have 1 O or 0 O. So I put here an OR between O and null, followed by plain. And if we look at this one, this airplane is matching this pattern, and this airplane also matches this pattern, but this one doesn't, because this one has 2 O's, so it doesn't match this regular expression. So if you're not familiar with regular expressions, I recommend that you look it up, because it's very useful for doing advanced searches and advanced search and replace in text. So when we look at this, there's some assumed spatial adjacency. You know, this one followed by this one, followed by this one, followed by that one, kind of goes left to right. Of course, if you write Arabic or Hebrew, would go from the other direction. If I take this tree and I turn it 90 degrees and I put it tabulated, I have the same expression that I had here, right? So there's an AND on top, followed by an OR between A, and an OR between I and E, followed by an R, followed by an OR between O and null, followed by a plain. So this is I'm just showing here. Somebody's typing and I can hear the keyboard. So please mute your phone, mute your microphone. All right. So now I put a curly brace tool at the end of this expression, and I have here some made-up text based on Queen's Bohemian Rhapsody. And this two means that I'm looking for two of these following each other. And how many matches will we have? We will have 3 matches, because this one adheres to this whatever's in the parentheses, and there's 2 of them. So this one and this one, they both adhere and match this, and the 2 of them they do. But this one is just by itself, so this doesn't match because you're looking for 2 of them. Right? So it kind of shows you that you can make this combine these expressions and make them more and more complicated. So it's formal, means it's computer readable. It's non-ambiguous. It's expressive, so you can express a lot of interesting things with this, like multiple iterations, numbers, letters, combinations, whatever. It's compact and can be typed by non-programmers. So folks who are chemists or physicists, they do use regular expressions even if they're non-programmers, because they learn this little language and they can express the search that they have. So wouldn't it be nice to have a similar language for VLSI layout patterns? So if you want to search for a certain combination of layout objects in physical design domain, how can you express that? With a similar language that's compact and expressive and non-ambiguous and formal and whatnot. And this is what kind of drove the motivation for developing this language. So I'm going to walk you through a series of examples. So I don't know, just asking, should I take questions along the way, or do I talk 50 minutes and I take questions at the end? Well, let me know what's the best way.
Questions at the end, please.
At the end. Okay, good. So, so here I have some rectangles, some blue rectangles, and let's say they represent metal 2 wires. And I give it a type. So type, let's call it a fuselage. It's a wire, and it's on metal 2, and its orientation is horizontal. And the delta y is 10. It means that the width is 10 units, 10 nanometers, 10 microns, doesn't matter what it is. And I create something pattern airplane, and I say there's an end here. It doesn't make much sense to have an end here, but you'll see later. For now, just ignore this end. And we are saying that there exists a fuselage called F, or F is a fuselage. So there exists a fuselage called F. Okay, and I will get 6 matches, because this one is a fuselage, this one is a fuselage. They're all on the same layer. They're all on the same width. We got 6 matches. Okay, nothing controversial here. Then I'm adding a constraint after this expression, or after this statement. This bar is, you can read it such that, is also called a guard expression. So whatever is in this dashed rectangle is a guard expression, and adds extra constraints to this object. And here I'm saying delta H, which is, delta H is the X value, is in this mathematical interval set from the curly brace to the curly brace. It means that it has to be exactly 70, or between 100 and 120, or 140 exactly. And if you don't know mathematical expression, you can look it up. It's on Wiki. So it's a way to compactly describe values and intervals. You can also use open parenthesis, which is strict, or square bracket, which is non-strict. So in this case, we only have 5 matches, because this particular wire had the delta H of 90, and 90 is not in this interval set. Had this been 70, it would have matched, because 70 is an interval set. Okay, so let's add a bit more to this airplane. So let's add the wing. So here I'm saying that there exists a fuselage called F with these constraints, and there also exists a wing called W with these constraints. And I'm going to walk you through these 3 lines of what these are. But we have to add another type. Let's say type wing, wire, let's say, is on metal 1, orientation vertical. I didn't give it any width constraint. So I'm drawing it with orange. So we have three statements here, or three constraints following, and they are by default ended together. So the logical end between these three. So I'm saying that the delta V of the wing has to be between 70 and 100, which means this dimension, the vertical dimension, has to be from 70 to 110. W.y center equals, so the wing's y center, same as the fuselage's y center, means they are centered along this centered line. And also, the fuselage contains the wing in the horizontal projection. So if you project this down to the x-axis, you're going to have a projection of the fuselage, this long, and the projection of the wing, this long. And the projection of the blue contains the projection of the orange. This is this line here. Now, if we look at how many matches do we have, we get those 5 matches. This one doesn't match because, first of all, it doesn't match this statement, as we saw in the earlier page, and it also doesn't have a wing, so this doesn't match. This one may be the right size, but doesn't have a fuselage. And then these 5 match properly. Okay, let's take it one step higher. So let's add the cockpit to the airplane. So now we are saying there exists a fuselage called F with this constraint. There exists a wing called W with these constraints. And there's a cockpit. Let's say cockpit is typed as VR2. Okay? So P is a cockpit such that the fuselage has to contain the cockpit. And wing doesn't intersect the cockpit. So I don't want the wing and the cockpit to intersect. I didn't say the cockpit should be on the left or right side of the wing, but it's saying that fuselage has to contain the cockpit, and the wire is not allowed to intersect the cockpit. And if you look at the drawings there, we're going to have 5 matches. Had this cockpit been moved here on top of the wing, it would have not matched. Okay, what else do we need for the airplane? We need a tail. So let's add the tail to the airplane. We have tail, let's say, in method 3, orientation is vertical. And I put here that tail.yc equals, so the tail's y center is the same as the fuselage's y center, so they're also centered. If you want to have an asymmetric airplane, then you could remove this constraint. And same as above, that the fuselage's horizontal projection contains the tail's horizontal projection. I didn't say that the tail is not supposed to touch the wing, or the tail has to be on the other side of the cockpit. So if I were to move the tail from here to here, it would still match. It would be an ugly airplane, but it would still be an airplane. If I wanted it to be on the opposite side of the wing, so the tail on one side and the cockpit on the other side, I probably should have added one more constraint here as a third line for the tail. We have 5 matches here. So I'll give you like a second to kind of see and absorb this. Okay, moving on. I'm creating a pattern, wing with engines. So forget about the airplane for a moment. I'm looking for something which is called wing with engines. Well, what is it? Well, it has to have a wing. It has to have 2 engines, E1 and E2. Notice on the same line, I can add multiple of these variables. Type engine, let's say engine is matter 4 oriented horizontally. And this line says that the wing contains this in the vertical projection. So if you project the orange line to the left, to the vertical axis, that projection has to contain the projection of the first engine and the projection of the second engine. This keyword is basically a placeholder for E1 and E2, means both of them. And then also, this contains wing in the horizontal projection. If we project it to the x-axis, the projection of the first engine has to contain the projection of the wing, and the projection of the second engine has to contain the projection of the wing. This is this second line. And also I want to kind of center these at equal distance from the center of the wing. And there's a rectangle. I'm going to draw the general intersection between E1 and E2. So this is E1, this is E2. And the way I outline this red line, my laser pointer makes a rectangle. That's called the general intersection between those two engines. That one is a Y center here, which has to be the same as the Y center of the wing. So this is a wing with engines. This is also wing with engines. And this is also one that's also, this is not, this doesn't have engines. This doesn't have engines. So if you look at the match, these three will match, and that will also match. The fourth one will match. So I think up to this point, there was nothing controversial or difficult. But on the next page, there's going to be something, there's going to be a leap of faith. So it's kind of a puzzle. So let's create a pattern called glider. And now I'm using the patterns that I previously defined. I defined an airplane and wing with engines and say, there exists an airplane. So this line would match all 5 airplanes. This one, this one, this one, this one, and this one. Because remember, the airplane had 4 components: the fuselage, the cockpit, the wing, and the tail. And it doesn't exist a wing with engines called W, such that W.W equals A.W. Well, this first W is a wing with engines. .W, this is a scope resolution operator, and gives me a scope inside of scope of wing with engines, gives me the wing. So if this is W, the wing with engines, then the orange is the W.W. And I'm saying that a glider, there must be an airplane, and there cannot be a wing with engines whose orange matches my orange, right? So this guy is an airplane. There's no wing with engines whose orange matches my orange. This one is also an airplane, but there is a wing with engines whose orange matches the airplane's orange. So this is not a glider. This is not a glider. This is not a glider. So we end up with 2 gliders. I'll give you a few seconds to kind of absorb this. Most of the time when I give this presentation, this is where people have lots of questions. Okay, let's move on. Now, now you can figure out how to create a jet. So if I want to match the jets, these 3, and not the gliders, what do we have to do? Is we just remove the knot. So now I'm saying there's an airplane. This would match all 5 of them. And there's a wing with engines whose orange is the same as the airplane's orange. And we get 3 matches. Okay. Now I'm going to go to the add a bit more beauty to the jets. Let's add windows to them. Let's say window is via on layer 1, via 1, something like that. So the first 2 lines is the same. I have an airplane, and there exists a wing with engines whose wing the same as the airplane's wing. And I'm creating a set here. Let windows equals a set of windows. This is a type. This is a set of that type. And in order to be a member of that set, that means that this airplane, A.F, the airplane's fuselage, has to contain the candidate element of this set. This guy, this keyword, is referring to one of the elements in this set that we are building. Okay, so we create a set for this airplane, and then we count how many windows do we have. You have to have between 3 and 5, so you can have 3 or 4 or 5. If you have less than 3 or more than 5 windows, then this is not a jet anymore. And we do have 3 matches because all of them have windows, and all of them have windows between 3 and 5. Then I'm moving on, and I'm adding a grid. This grid is defined on this line, and this has an offset and a period and an orientation. And I'm going to draw the grid. It's a bit faint. Hopefully you can see it on your screen. And I added one more constraint to the set. Remember this one saying that the airplane's fuselage has to contain the window for it to make it to the set. So if you're talking about this airplane, the set of windows is this one. That set doesn't contain this window because it's the fuselage, the blue fuselage, does not contain this window. And I also say that this .x center has to be on grid G. This is the grid G. So that means the center of the window has to be on that grid. And notice that this is on, it's not perfectly drawn because PowerPoint did some snapping, but these are on grid, these three are on grid, these four are on grid. These two are on grid and this is not on grid. So this is off grid. So the count of in this set of these windows will be only 2 here. And the count will be 4 here, and the count will be 3 here. As a result, we're only going to match 2 jets. Moving on. So let's take it even higher. Let's create a formation. A formation is built of 2 airplanes, A1 and A2. The type of A1 is a jet. The type of A2 is a jet or a glider. So we can have a jet-jet or jet-glider. Those are the formations possible. And we also have to have some constraint between the distance between the cockpits. So A1 is a jet. A1.A is the airplane in the jet. If you remember, we had this, what is a jet? Well, a jet has an airplane and the wing with engines, so this stuff, right? The airplane has a wing, so we can say go from jet to the A, which is the airplane, dot W, which is the wing. So here I'm saying A1 is a jet, A is the airplane inside of the jet, P is the cockpit of the jet. Euclidean distance to A2, which is this guy, dot airplane, dot cockpit less than 60. And notice here we have a formation between 2 jets, and we have a formation between a jet and a glider. And indeed, their distance is less than 60. So this Euclidean distance is a member function of this language. Of course, now with the COVID-19, we have to add another function called social distance. We don't have that function yet. So we have 2 matches. We have 2 formations. These 2 airplanes don't make a formation because the cockpits are too far away. If I would move these 2 airplanes up higher, at some point this cockpit would get close enough to the other cockpit, and another formation would show up here. These 2. Now let's go one more step higher. Let's have a relationship between formations. I call it close formations. So F1 is a formation, F2 is also a formation, such that their bounding boxes intersect. So again, F1 is a formation, F2 is a formation, such that their bounding boxes intersect. And I add one more thing here, that there doesn't exist an airplane, a 5th airplane. I mean, this formation has 2 airplanes in it. This formation has 2 airplanes in it. And let's have a 5th airplane, and I don't want that to exist if it's less than 20 vertically from the box of the first one, or less than 20 vertically from the box of the second one. And I walk you through it, how this is evaluated. It's a bit complicated, but bear with me. So this is the bounding box of F1. This is the bounding box of F2, and this is satisfying this condition on this line. Okay, then we have this 5th airplane, this little A guy, right? This is A. Its spacing is 40 from the F2 bounding box and maybe 200 from the F1 bounding box, vertical spacing. So both of these are false. This less than 20 is false, less than 20 is also false. That means that the OR is evaluated as false. There exists an airplane such that is false. The not is a negation of that, and that is evaluated to true. So we have this is true, this is true, this is true. So the rule or this rule will evaluate to true. We get a match. So the whole rule is evaluated to true. And that's why we have a match here. Now let's see, we take this airplane and we move it north a little bit. We move it north to a point that it gets close enough to this F2 bounding box. As I said, I move it to 18 distance. Let's evaluate now this whole rule. So it is, this will be true because the distance to the bounding box of the airplane A spacing vertically to the F2's bounding box is less than 20. This is true. This is false. So the OR is evaluated as true. There exists an airplane with this condition is true. The not negates that, and that returns a false. And the whole rule is not matching, so there's no match here. So if you recap of how many concepts we have here, we have the basic types, the wire or the fuselage or the wing or the cockpit. Imagine in VLSI this could be metal 2, this could be metal 1, this could be VRT, this could be VR0, this could be metal 3, whatever, right? So it can be any type. It could be even in architecture. You could have a walkway or an aisle or a street or a building or whatever. It could be 3D solid objects. It doesn't have to be only VLSI. As long as you have these rectangular shapes or rectilinear polygons and relationships between them, you could express any kind of constraint. So we use those basic types that we defined on top of the code here. We use those to create an airplane concept. And then from the airplane, then separately we did the wing with engines. Then we use those two to differentiate between jets and gliders. Then we created formation, which is a pair of airplanes. Then we created CloseFormations, which is 4 airplanes basically in some relationship. And then we have a 5th airplane which can, disturb these 4 airplanes flying peacefully and then, match certain pattern. So I don't know of any language today that it can express this efficiently and elegantly. If you were to write a checker for this to actually recognize this pattern with polygons, it would be a huge amount of work. A huge amount of work. Bloating, shrinking polygons, and doing this measurement and that measurement, it would be really, really, really difficult. It could be done. It's almost like writing a chess program in assembly language. It can be done, but it's like huge, huge effort. But there's also another thing. So this is a checker. So we check if there's some layout and we want to find this close formation, then we match it. But the magic is that once you have this logic written, you can actually synthesize layout from it. And I'll show you that one. So I simplified that formation a little bit. So I have the formation as earlier. We have an A1 and A2 airplane. A1 is a jet, A2 is a glider. And we have the distance between the cockpits less than 60. And I just said that closed formation simplified, I have 2 formations such that their vertical spacing is between 150 and 300. Not less than 150, not more than 300. And we have an engine that actually generates a layout from it. And it did have the airplanes. So one is a jet, one is a glider, one is a jet, one is a glider. The cockpits are appropriately spaced between less than 60 apart. And so this can be used for test generation. So once you have the logic of the rule in mind and you write it down, then you can push a button and automatically you generate layout and more layout. This is 50 here. So we did these things here, and this is 280. So this adheres to the proper spacing, and this adheres to the proper spacing. And then we can generate more layout and millions, right? So there's no limit to how many of these patterns can be generated. Notice there's no constraint whether they point in the same direction or opposite direction. There's no constraint that the engines may or may not intersect the other plane's wings, and all of those constraints could be added. So if you've written that match and say, well, I don't want this is really not a formation because here the wing is touching the engine, right? Then what you would do, so if you want to avoid this one, I'm going to show you how to do that. You would go to, I'm going to go to no presentation mode now. You would go to a formation here. So here we have A1 is a plane, the other one is a, then you would say, you know for sure that A1 is a jet, right? You don't know about the other guy. So the other guy may or may not have engines, but this one has engines for sure. So you could add the following. You could say that A1, which is my jet, dot A, which is the airplane, dot wing with engines, like that. No, excuse me, no, it's not. A1 dot wing with engines dot E1 dot intersect A2 dot A dot wing, like that, and we'll put a big knot in front of it. Right. So A1 is a jet, and the jet has a wing with engines, and that has an engine E1, and I don't want it to intersect. And of course, I could do another line for this for E2, because I don't want neither E1 nor E2 to intersect the other guy's wings. And then if you added this line, the test layout generation would not create this kind of test layout here. It wouldn't create this kind of layout here. And there's more test layout. So I'm just showing a few examples here. Okay, so why I do this thing? Well, from experience, we know that when people define rules, design rules, they have some thought in mind, you know, based on lithography, on OPC, RET, whatever. They have some rule in mind that they want to impose. In the past, those rules used to be relatively simple. You had a spacing between two wires, or a V enclosure, or some landing rule. But with this, really we're pushing the envelope of the technology, and the rules are becoming more and more complicated. And then it's hard to express them, or whatever's in the head of the person, it may be interpreted in the wrong way. So when they write the rule in English, it leaves a lot of room to interpretation. So imagine if you had to write this rule with the airplanes and the formations in English, and then give it to somebody else and say, hey, create some layout based on my description. It's going to be very difficult to fully understand what they wrote and follow them. So, if it goes from that English to run set code, the run set code which is a checker, may or may not implement what the original thought was in the yellow person's head, or the person on the very top left. So it is formal, it's machine readable, it's complete, it's imperative, it's not human consumable, and may not encode the original intent. It's very hard to reverse check. Did this checker implement the original intent? Then if you have to create test layout, again, you need another person. You need this person to write a run set, you need this person to write a test layout. And then if you want to have some kind of algorithm developed, let's say with a set solver, set means a Boolean satisfiability solver. Renato, the person I mentioned earlier, he's like an expert in that. So if you want that, then you have another person to interpret that. And if you have some tool, let's say some EDA tool that needs a text file or some kind of collateral to be able to obey the rule written in English, you need another person to convert that. There's a lot of ambiguity and effort and questions and all that in this path. It's not the most elegant and efficient way. So if you have this declarative language, you have the rule expert and can write the intent in this formal language, formal declarative language directly. And that opens the possibilities for automatic conversion. Let's say you can have an online checker, you can have a test layout generation, you can have a set solver. It's even possible, in principle, to generate the orange run set from the yellow. We haven't explored that path yet, but this is a declarative language and this is a imperative language. In principle, it would be possible to do automatic conversion. Also, for example, you need some collateral for a router or place or something. That also could be auto-generated. It's not easy to do these arrows. I mean, it takes work, but it's a one-time thing. Once you do it, it's like a compiler. You go from C++ to assembly code. Once you write a compiler, then millions of people can operate in C++ level. They don't have to operate at the assembly code level. So you can have automated paths. So what is this language? Well, it's a declarative language. So declarative versus imperative, I kind of touched upon that. Declarative is, think of like a mathematical expression when you are saying what, not how. So when you are saying A plus B or C equals A plus B, that's a mathematical expression. And you're not saying how you should do the addition or the assignment. You're just saying, I'm saying the truth, that C it must be equal A plus B. An imperative, on the other hand, it actually does the implementation. That's the how. So it comes from the word emperor, and the emperor says, take the stone, move it there. Why? Because I told you so. Other guy, take the stone, put it on top of that stone. Why? Because I told you so. And you keep doing that, and eventually a pyramid appears, right? Because the emperor kept telling them to do things, and eventually some end result appears. You can have, for example, you want to do addition or multiplication. You can go and do binary shift. You can take your binary number and shift it to the left, shift it to the right, do XOR, bitwise XOR, whole bunch of things, and eventually end up with a result. That is imperative because it takes some value, some numbers, or takes some polygons or geometries and keeps changing them and blows them and shrinks them and XORs them and slices them and subtracts them. And the end result, you end up with something called a marker, which is kind of like the residue of all these operations. And the existence of the residue tells you that there is a violation or match happened there. That's imperative. The declarative, it says, I'm looking for a truth. And the truth is that there exists a wing, and the wing is not in the fuselage or whatever. And then there's no state changes. You're not saying, let me take the wing and blow the wing by 10 and then shrink the wing by 11 and then subtract the wing from the fuselage and all that. So there's no state changes. And there's a theoretical path from declarative to imperative. and going from imperative to declarative is near impossible. So imagine C++ and COBOL. Both of them are imperative languages. Taking an automatic translator from COBOL to C++, to take 1 million lines of COBOL and translate it to C++ automatically, or going from C++ to COBOL automatically, it's impossible, basically. But if you have an expression, a mathematical expression, you want to convert that to C++, that's possible, no matter how complicated the mathematical expression is. So that's the power of declarative languages. It can convert to other models. So it can go from declarative to declarative, can go declarative to imperative, can go to set solvers or SMT solvers, and then those can help us generate test layout. So it's formal, it's computer readable, it's compact and expressive. You have seen how I was able to express these complicated formations with a relatively few lines of code. I've taught this language to many people, and they can learn the language in 2 hours, 2-3 hours. If they really want to learn it, they can learn it so that they can write. What I showed you, I can teach a person in 3 hours to learn. And also, our goal was to support rules of any complexity without the need to change the language. So let's say a rule comes up that you cannot have layout that looks like the Eiffel Tower in Paris. We can use this language to search for patterns that look like the Eiffel Tower without the need to add new concepts to the language. I'm not saying that the language is fully complete. If I don't really know how to check for layout that looks like the Fibonacci series or something like that. So I don't have a proof that the language is complete. But we have been challenged with very difficult rules, and we were able to do it. So we want to have this as like the de facto language of rule communication, either human to human or human to machine or machine to machine. It has a bunch of geometric functions. It has support for polygon sets, as long as they're rectilinear. And then you saw that we have these patterns, nested patterns, exceptions, custom functions, grids, sets, elements of sets, subsets, and a whole bunch of stuff. And we are using this language within our company. I cannot elaborate at what level, how, because that's internal information. We also open source it under SI2. SI2 is the Silicon Integration Initiative. That's a consortium that Intel is a member of. And we open source it under the name Opal. That was a couple of years ago, so the code that they have there, it's a bit older version. And it's been sitting there, so it's kind of on a dead end right now. There's not, as far as I know, nobody's really using it yet. So that's all I had, folks. I'm ready for questions.
So thank you for this nice talk. We are open for questions. If you have questions, you can type them in the chat. I have a question now. Does your language support multiple patterns? For example, I can have shapes in the same layer being assigned to different lithography masks. So for example, the rule will be something, if the distance between two shapes, the minimum distance must be X, for example. But if they are assigned to different lithography masks or different colors, the distance can be smaller. Is it easy to express this in your language?
So let me see. So let's say we have two objects, A and B, right?
Yeah.
We have two objects, A and B. And you're saying that if they are different, let's say they're both yellow, right? We want to have some kind of spacing constraint between them. But if it's
Yeah.
orange and yellow, we want to have a different spacing constraint, correct?
Yeah, that's the question, yeah.
Right, right. So that color, you can think of it as a type. So let's say this is metal 3, metal 5, okay? Or diffusion versus Tician or something like that. If you know the type, then you can write the rule type-based. You can say, if I have a Tician and a poly, the spacing is such and such. If it's poly and poly, then the spacing is such and such. Or you can have properties on these. So for example, you can add a property to the type. And you can say, let's say name, okay? If this, or month of birth. If the month of birth is January, in January, the spacing is 100. If the month of birth is different, then the spacing is 120. Did I answer your question? You're breaking up a little bit, and I'm not sure I fully understood your question.
I think so. I'm not sure if I understood how to implement this. But the question was, in general, if I can write multiple pattern rules easily with your language.
Yes, but I still want to, maybe you can put it in the chat window, because you were breaking up a little bit.
Okay.
So if you put it in the chat window, I can write right now. I can actually show it here.
Okay, so while I type that, I think I can
Go ahead.
questions.
Go ahead, please.
I will ask a question from another person first. So, is it okay?
Okay, fine. Yes.
So Mateus Fogassa asked, is it really the OPAL Opal?
Opal. That's the name of this language under SI2.
Yes. Is this related to Opal? Is the language related to Opal?
Yes.
Okay.
Yes. So this language is the same as Opal, basically.
Okay.
We just developed it further within Intel. And what Opal is an earlier snapshot of this language.
Yeah. Is Intel contributing to, for example, CI2, Open Design Rules, Open PDK kinds of efforts, in which case it could be seen?
So if I understand correctly, the question is, this is the still through SI2, right? This is the SI2 efforts for rule modeling. So there were some OpenDFM efforts and others in the past, and Intel was involved in those. I don't know the latest status on that.
Okay. Is this currently tied into a production DRC checking capability?
I can't really comment on that because this is internal information.
Okay. And how do you feel about usability for pure play foundry processes, which have more complex DRs, as far as I know, than Intel Foundry?
I'm sorry, can you repeat the question? Are you breaking up?
Yeah, the question is written in the chat. If you can read, it's the number 4 from Mateus Fogassa.
Please put it in the chat. So the chat is, oh yes. How do you feel about usability for pure play foundry processes which have more complex DRs, as far as I can tell, than Intel Foundry? So as far as I can tell, if the rule involves n objects that all have rectilinear edges, vertical, horizontal edges, it could be rectangles or polygons or polygon sets, we can model the rules, right? Now, you could come up with something super complicated that you want the rectangles to be ordered based on Fibonacci series or something else. I don't know. So you can probably come up with a super duper complicated rule that we cannot support. But you can do like a if you want to have a rule with 15 objects with all kinds of relationships or hierarchical relationships, patterns of patterns with exceptions, we can support all of that.
Is this open for questions? It is, right?
Yes.
Gyuszi, this is Renato.
Well, I see that there's a... Yes.
Hi. So,
Yes,
Gyuszi, can you comment on your plans for what is published about this language? Are you planning to publish the detail? Well, I know that SI2, it's an old snapshot, but are you... Tell me what are the external publications that you have or have planned? Like, do you plan to publish the document of the entire language? Or do you plan to re-engage with SI2?
Yeah, so actually, good question. So when we did the submission to OPAL, to SI2, we did give them the whole code, and we gave them the whole reference manual. Again, this is almost 2 years old now, so since then things have evolved. So what happened at the time? So actually, we went to the board of SI2 board. We presented them, and this was inside SI2. There's a group called the standardization group, and we went to the board of the standardization group. And I think there was a confusion, and I actually see a question right now in the chat window that's relative. That will this be a caliber killer in a few years? I won't say that. No, this is. I think this is. Think of it like mathematics. You know, it's bringing in a means of describing the intent of the complex rules in a precise manner. It's not intended to be a production like a super checker that can operate on millions of rectangles on, you know, it was never intended for scaling at that level. It is intended to capture the most beautiful way and most concise way the intent of a rule, and then act as a gateway for automatic conversions to either run set or test generators or whoever wants to convert in anything they want. So at the time when we presented this to SI2, the question was again, well, is Intel using it? Can you make a statement? And no, we couldn't make any official statement, and we still can't. And then, you know, how does it compare to run sets? And I think there was a bit of confusion. So it was not adopted as a standard. And I think if there would be interest from the SI2 community, that effort can be rekindled. The person who mentored from SI2 retired in the meantime. So we'll have to, you know, re-establish those relationships, all that. So we are open to that, but I'm not going to push for it. You know, I have plenty of things to do, so I'm not going to be proactively pushing for it. If there's need, we'll do it. If there's no need, we won't do it.
Okay, we have another question. Will this be a caliber killer in a few years?
That's what I just answered, that question. Right now.
Okay, sorry. Now, if there is time, I can give you my question again. I just wrote it.
Yeah, I can. Yeah. Go ahead. So there are two shapes in the same layer. If the shapes have the same color or same lithography, they must have a minimum distance x. And if the colors are different, then the maximum distance can be, the minimum distance can be smaller. Right. So, for example, you can. I'm typing in my window here. Let me put it in Courier New. Okay, so I would have something like rule R1 and So we have two objects. I call it A and B of type and let's say matter. Okay, like this. Matter 4, matter 4A, matter 4B, and Renato, my friend. So these are all types. What is a Renato? Renato is some rectangle that represents something. Okay. So we have these two. So we want to say A dot spacing to be, let's say in the horizontal dimension, is less than some value V. Okay. But this value V depends on the type, right? If it's Renato, or if this is this or that, it may be different values. It may be different than if A is of one type and B is of the other type, right? So then you can say it's less than, let's say, mean dist of A and B. So I just created a custom. Let me just put it in Courier New. I don't like this font here. Here we go. Okay. So I just created a custom function mean this between A and B, right? And I'll show you how to write that. Okay. So here above I will say define. Come on. Define mean dist between M and N. So those are the formal argument names. Okay. And here we say let R equals. Okay. And now, so now I have to say, so here I have to put, say if, let's say, M dot type equals N dot type, then it's 100, else it's 220. Okay. Now this is a very simple thing. But then this could be more if statements, right? It could be if it's M4, M4A, or whatever. So this function can become arbitrarily complex, right?
Yeah.
And then this relationship here is like that, right? Another thing that you can do is the following. Rather than writing it this way, you can have a rule R like this. So you say Control C, V, I call rule 2, and then if I limit the types to A and to this M4 and M4A, whatever those types are, then I know that the distance is gonna be less than 100, whatever. And then I can write another rule R3. Which is, if they're different types, let's say, my typing is very slow for some reason, the network is very slow like that. And if this is a type NR2 and R4, then the value is 200, something like that. So it can be done in multiple ways.
Yeah, thank you.
Did I answer your question?
Yeah, sure. Okay, so Ricardo asked if you can say something about something to the students who want to work at Intel. Which skills do you consider?
Yes. So Intel is a big company, right? So obviously, you know, there's many needs. I recommend Intel. It's a good company. It's, you know, many groups, and different groups have different cultures and different dynamics. You know, there's many very good groups at Intel. In my area, I was looking always for people who are good at math and good at programming, then we can teach them about you know, electrical engineering or other stuff if they're good at those skills. So I'm usually looking for puzzle solving, spatial puzzle solving, mathematics, programming, recursion, object-oriented design. Those skills turns out that they are very useful. And because we are, at least my domain is about physical design, where we have to deal with rectangles, polygons, distances, mathematical logic, all of that, and encode these sophisticated algorithms. Those are the skills that I'm looking for. Of course, you can go to other domains. You know, there's people who go to design and all they do is electric engineering or running EDA tools, or you know. But I've been in the area of either CAD development or design model development or language development. So that's my answer. And I highly recommend, if you can get an internship, try it. And Nato was an intern at Intel, and he had a very good career there. So send us more Brazilians.
Yeah.
Yes.
We have one last question from Altamiro Suzy. He says, congratulations,
okay.
I tried to write that data path assembly. How do you assure correctness? Let me be precise. It was in the early 80s. I failed to be confident to the correctness of the resulting structure in complex constructions. It is written in the chat.
Okay, so yes, I see the chat window. Yes, I see the chat
okay.
window. So so if I understand correctly, the person tried to create a tool that did data path synthesis. I assume placement or routing or something like that. When you create layout, you need to have some model that models the design rules, right? There could be hard-coded in C++, which is not the preferred way, or you can have them in some kind of lookup table, or have it some kind of like in this language that I presented today. And if you have that model correct, and you build that model into your synthesis tool, then by design you can guarantee that your layout will be correct. Of course, you can use things like linear programming, or you can use set solvers or SMT solvers or other tools or other engines to make sure that those constraints are obeyed during the synthesis. So Rafael, I assume, I hope I was able to answer your question.
Yes. Does anyone have a question? I think we are going to end.
So, thank you very much, Gyuszi. It was an excellent talk. Thank you, Marcus, to chair the session. It was a pleasure to have your talk directly from USA. Thank you very much. I hope to see you in person here in the south of Brazil in the near future. So thank you very much.
I will go. If you invite me, I will try to go. Thanks for the opportunity. And, you know, let's keep in touch.
Okay. Thank you very much.